Okay. Okay, thank you so much. Hello, everyone. Welcome to my presentation. This is Younes Mohammadi from Federal University of Rio Grande do Sul of Brazil. The title of our work is Impact Evaluation of Neural Grounding Resistance on Short Duration RMS Voltage Variation. Next slide, please. Yeah, a table of content, introduction, computation of voltage under unbalanced ground fault condition, I mean line to ground fault and line to ground fault, analytical evaluation on an industrial system, and then conclusion. What is neutral grounding resistance? Enter, please. Neutral grounding resistance limits the magnitude of the ground fault current because influences the total zero sequence impedance and then impact on the voltage during ground fault. Short duration RMS voltage variation, interruptions, sags, and swells. Interruption when the voltage is smaller than 0.1 per unit. Sags when the voltage is between 0.1 per unit and 0.9 per unit, and swell when the voltage is between 1.1 and 1.2, 1.4, 1.8, depending the standards. Next, please. So in this work, we present evaluation of influence of neutral grounding resistance on short duration voltage variations during line to ground fault and line to ground faults for an industrial system. Please consider a radial system like this that is so common for calculating the voltage sag. ZS is the impedance of the system, ZF impedance of the feeder, and we have the PCC point of common coupling for the measuring. For the line to ground fault, we have three networks, positive, negative, and zero, that they are connected series. We can calculate V1, V2, and V0. For example, for V0, zero sequence voltage, we have two parts, and in the second part, we have V neutral. That V neutral is included 3 Rn per the equation. And next, please. Okay. Okay. And for the line to ground fault, we have three network again. Positive and zero network are connected parallel, and they are connected to the zero network parallel. And in the zero network, we have 3 Rn that's connected series to the 3 Rg. Rn is the neutral grounding resistance and Rg is the fault resistance. And in both of them, as you can see, R0 is Rn plus Rg. Enter, please, Professor. Okay. So, it's the system, the case study we considered. In this system, neutral grounding resistance is 270 ohm. Enter, please. Okay. For example, for a fault, for a line to ground fault, at the end of the feeder and the point of common coupling in the secondary of the transformer, we have a voltage for A, B, and C. We have a voltage sag for voltage A and voltage swell for voltage B and C. And the neutral current that is not too high because in this case is equal to the fault current. Next, please. Okay. The result of the phase to neutral voltage and phase to phase voltage against of neutral grounding resistance for different value of fault resistance will be shown here. For example, in the Fig 5, for the phase to neutral voltage and line to ground faults, the voltage change with neutral grounding resistance lower than 10 ohm. By fault resistance 0.5 and 1 ohm, there is a very severe voltage sag at phase A when the fault resistance is 0 ohm and neutral grounding resistance is very small. For another fault resistance, the voltage sag are shallower. Shallow voltage sag occurs in phase B and no voltage sag occurs at phase C, but voltage swells are seen at phase C. For neutral grounding resistance higher than 10 ohm, the voltage magnitude are equal to 1 per unit. In the figure 6, similarly for the phase-to-phase voltage and line-to-ground faults, voltage A, B, and C are affected when the neutral grounding resistance is lower than 10 ohm, and the voltage variation are more remarkable for fault resistance 0, 0.5, and 1 ohm. Severe voltage sag at voltage AB is for fault resistance 0 and 0.5 ohm, and at voltage CA, severe voltage sag is for fault resistance 0 ohm, and also voltage swell for fault resistance 0, 0.5, and 1 ohm. The magnitude is 1 per unit when the neutral grounding resistance is higher than 100 ohm for voltage AB and CA, while the magnitude will remains 1 for the VC voltage. Next, please, Professor. Here we can see this. Okay, no problem. Okay, for the phase to neutral voltage during line to ground fault in the figure 7, we have a severe voltage sag at phase A when fault resistance is 0. On the other hand, the voltage magnitude remains close to 1 for any values of neutral grounding resistance with other value of fault resistance. There are severe voltage sag at B and C phases also for any value of fault resistance and neutral grounding resistance. For the figure 8, for the phase-to-phase voltage and line-to-line fault, there are severe voltage sag again for voltage A, B, and CA when the fault resistance is 0 ohm, while for other value of fault resistance, the magnitude remain 0.85 for voltage AB, and extreme voltage sag for BC voltage are found for any value of our neutral grounding resistance. Next, please, Professor. Okay, here we have some recommendation for the loads. For the single phase load and for the single phase load with the phase to neutral and phase to phase connection, we have a less severe voltage sag if the neutral grounding resistance is between 2 and 10 ohm according to our simulation. No voltage swell will be observed. For the three-phase load with phase-to-phase connection also, we have a better performance against short duration voltage variation with an neutral grounding resistance higher than 10 ohm. And as an overall result, for the system with low resistance grounded and the load connected phase-to-phase, we have a fewer short duration voltage variation. Conclusion, neutral grounding resistance influences the magnitude of phase to neutral, phase to phase, and also phase to ground. We didn't bring phase to ground voltage on the simulation, on the presentation because of time limitation, but yes, neutral grounding resistance can affect on the voltage, on the phase to ground voltage also, but it's so similar to the voltage phase to neutral. So being the influence higher when the fault resistance is low. For the voltage type phase to phase has the best performance for the short duration voltage variation caused by ambulance ground fault, line to line fault, and line to. And loads in a low resistance grounded system may experience fewer short duration voltage variation also. Next, please. Okay, thank you so much for the presentation. And sorry, I got some problem about my connection, and Professor Zia helped me a lot. Thank you so much, Professor.
Well, thank you. Thank you for the presentation, Younes.
You're welcome.
We will sort of open the floor for questions, really. If anybody has any question, please, now it is the time.
Okay.
I did not get anything through the chat box. Let me just double check it. No. Any questions for Younes? Seems none. Okay. So what I will do, I'll bring in the this one, I think. Back to the conference screen share, I think. And I can turn on my camera. So overall, thank you very much, Younes. I don't think there was any questions there for you.
You're welcome, Professor.
We had overall 7 papers. I'll just ask whether there is any question for the Professor Drapela. I think it was on paper 79 because we didn't allow any questions for that paper. Does anybody have any questions regarding the presentation for paper 79? This was the battery storage and charging systems, power control, and supporting the voltage and the charging. No questions for that paper either. So thank you. Overall, we had 7 papers ranging from resonance to sort of stabilization of the various lamps. Then we went and explored a bit on fault clearance time, critical clearance time. Then Oscar did a good presentation on the high frequency measurements. And then we had the capacitor bank switching, plus the neutral earthing, and of course the battery charging system. Unless there is any other question generally, we are pretty much done in this session. So thank you very much to the authors for their time and their presentations.